Hello, my name is Pablo Tenorio, and my teammates are Edgar Torres and Sergio Mendoza. We are going to present the infinite square wave problem in one dimension. First of all, let's talk about quantum mechanics. Quantum mechanics has been very effective to yield mathematical descriptions and predictions for systems where this new physics arises. However, it also yields results that are sometimes difficult to interpret given the intuition that we have developed by classical physics.
We are in the year 1924, after Louis de Broglie revolutionized physics by theoretically demonstrating that wave has particle properties and also that particles behave as waves. He unified the concepts of wave and particle, and his discoveries were such important in that time that Albert Einstein itself publicly supported his ideas and his new theories. But the concept that the electron was a wave was still unclear. And there was no way of calculating the time development of, of the electron. To solve this problem, in 1925, a young physicist, Erwin Schrodinger, deduced the fundamental equation for quantum mechanics. This equation is so important as in classical mechanics, the Isaac Newton's equation, force equals mass times acceleration. He also deduced the wave function as an attempt of generalizing the idea of a wave to matter behavior. He applied concepts of energy conservation and mathematical formulations for a wave.
Now, the wave function is a mathematical tool used in quantum physics, and it's used to describe the quantum state in an isolated system. It yields probabilities for any state of this system, and it's a complex probability amplitude represented by the letter psi.
The equations below are the wave function itself. Psi, a function dependent on two variables, x and t, equals the number e to the power of the complex unit I over h bar times the momentum times x minus the energy times t, where the momentum is defined as h bar times k and the energy is defined as h bar and omega. Here h bar is the Planck's constant, the reduced Planck's constant, that is its value divided by a factor of 1 over 2 pi. Then, from the wave equation, Erwin Schrodinger applied new concepts using the magnitude of energy and momentum as operators. And then with the conservation of energy, he deduced this beautiful differential equation of second degree. And from here, we can derive all the properties of the wave function.
To simplify things, we will use the Schrodinger equation in one dimension. This is because the calculations are much simpler, but still yield results that their interpretation and understanding is significant in higher dimensions. We use this equation below, and it is equal to psi times k squared, which is a constant, to simplify things. Now, the problem is called the infinite square wave problem, or more commonly known as the particle in a box problem. We will see we use the Runge-Kutta method to solve it. But first of all, the problem it goes as follows. We have a particle which can move freely in two limits, 0 and L. And then we have, beyond these limits, barriers where the particle cannot be found, where it has zero probability to be found. So that is why it's called a particle inside a box. These limits will be used as the boundary conditions in our differential equation, as we'll see later.
Now, in order to solve the Schrodinger equation, we need to, as we saw in slide 1, the discrete values for n integers of the energy, which are h bar squared times pi squared times n squared over 2 times the mass times the length squared. And we have the normalized eigenfunction psi sub n of x equals the root squared of 2 over L. This is going to be the normalized factor times the sine function of n times pi times x over L.
Okay, so these are the values that we are going to work with. The particle that we show use for this example of the particle in a box, the particle that's going to be trapped inside of this is going to be a proton. So then we will use the mass of the proton as expressed in mega electron volts over the speed of light squared. This is just to have symmetry in the units that we use. So that's why we use h bar also as electron volts, millimeters. And we will use a box of total length of 40 times 10 to the minus 12 meters, such that our limit will be, if we find ourselves in the middle, minus 20 and 20 to the right. Very well, so for the numerical methodology, we have chosen the Runge-Kutta method to solve this problem. This will be, here we will have a little explanation about what is the Runge-Kutta method and why we chose it, and then we will further explain how we did it. The method for solving the time-independent Schrodinger equation was chosen as the specifically Runge-Kutta method of order 4, because of our programming knowledge, the nature of initial value, differential equation of the problem, and the high accuracy versus relatively simple coding it yields and requires. So how does the Runge-Kutta method work? To derive the Runge-Kutta method, we consider this equation, this differential equation, where we have this interval, and then we shall now divide the interval into the interval AB into n's of intervals, such that we have x of n, then x of n plus 1, with n ranging from 0, 1 to 3, 4, and so on, and integrating y prime, this function, over this, and utilizing the mean value theorem for intervals, we obtain this equation, where we can we have now this term h. We'll call x of n plus 1 minus x of n. Also, as we can see, this function is has these terms xc and y of xc, which we have xc belongs in the set x sub n and x of n plus 1, from x of n to x of n plus 1. If we approximate, well, let me just go like this. If we approximate the function, which we have here, by the linear combination values, which would be f, this would be 1, and then 2, and then so on and so forth. On this interval, on the interval, we arrive at the general Runge-Kutta method, which is given by this equation. And now we can choose values for m, we can choose values for c and for xc, and we will have different computation formulas. The one we will use is this one, which is the Runge-Kutta method 4. and we will further explain how we used it. We will now go to the code section, and we shall explain it a little bit. First off, we said that we will have this equation, which I'm going to go a little bit back, which is the second derivative of psi over x squared is equal to this. As you can see, this is second order or ordinary differential equation. But here in the Runge-Kutta method, we used a first order ordinary differential equation. So what shall we do? We shall now convert this equation into a system of two linear ordinary differential equations. We have first the equation, the Schrodinger's time-independent one-dimensional equation, and we will now what we will do is this will appear. We shall define a new variable z, and we shall now describe the equation, the differential equation, as the differential z over x is equal to this part. Pretty straightforward, but now we will have a system of two linear differential equations. Okay, so here is the code. We have included these annotations with the exclamation mark for further explanation, but I should just run over it. We begin the program. We begin specifying implicit real, but it's taken with the double precision, and this is also because we want to be able to declare variables along the way, and not just like every time you have to go back and the program will tell you that you have to specify. We define these variables are defined for our method that we will see later, and the dimension is chosen as m equals 10,000, just because, I mean, we can run it, we can change this number, but we can run it like how big we can take the area. We now define the wave function psi. At boundaries we set is 0. Where the potential is infinite, the wave function is 0. So we define out c. This is the derivative. We take we don't take 0, but we will just take 0.001. A little bit of precision. We chose double precision as well. So we will see a lot of like this d float and d 0. Okay, now the box size, as we told, was 40 times 10 to the minus 12 meters, and we have here 20. I mean this is all scaled, so we will see like different values because in the program we can just like say 20. 20, this is meters and this is blah blah blah. Like we have to scale everything. So we have given this one for that, such that we get minus 20 and plus 20, such that we're like in the middle. Then this is the H step of the Runge-Kutta method, where we have our range. Our range will be like xi, xf, which is our boundaries, and the float NPTS. Well, NPTS we have given it for the accuracy. If it's the n sub-intervals, this is also changeable. And okay, so now we define our variable z1 and z2. Z1 is the wave function. Z2 is the differential of the wave function, and we will give the first value of x to be xi. So this minus our lambda. Now n state we have defined it as our eigen state, which is 0 initially, and the result, the outcome of this program will be to find the different eigenvalues for each eigenstate, for a desired eigenstate. That's why this program is changeable. We can change the box size, we can change the range, Here we define E for energy. Energy range from 0 to 40 mega electron volts. This is the 40, and this is divided by 1,000. This is also changeable, but okay. The next section will be the Runge-Kutta computation formula, which we have. I mean, the formula applied for our code, but in terms of our variables. Here we can see it more clearly, and well, we have now to say for when we talked about this case, we shall have two because we have now a system of these equations. Therefore, we need to have two defined carefully for each of the variables we have chosen. The x step will be xn plus h, and our end states, our eigenvalues and our eigenstates will be given by this final part, which is defined over all of this before. This is just an accuracy error, and we shall now, I mean, we tell the code to write the n state, which is the eigenstate 1, 2, 3, which is discrete 1, 2, 3, 4, 5, etc., and then the energy value, the eigenvalue. And finally, this is a function where we define function 1 is z2 as this, and we have function 2, which would be the minus 2, the mass of the proton times E times our initial z1 function bar squared. And we assign the proton mass the value of, as before, everything is calculated accordingly. So then we run the code for these initial conditions, and this is what we get: 1 through 17th eigenstates. For these energy levels are calculated as mega electron volts for the proton in each eigenstate. Here we have compiled a graph. We have plotted the eigenvalues in mega electron volts and the eigenstates, and we can see it's a beautiful quadratic placement that we have acquired.
Okay, well, in conclusion, the Runge-Kutta method was a great way to solve this mathematical problem and also gain a better insight into quantum mechanics. We obtained the 17 eigenstates successfully. So this was a great way to apply numerical analysis into our insight of physics.
Thank you very much, and that's all from us.